afternoon we're going to do matrix operations. Before you actually go through this material, make sure you read the PowerPoint/PDF presentation I gave you, so this won't all seem fresh. I'm not going to go through all of it. Today in matrix operations, we're going to cover how do you add, subtract, and two kinds of multiplication of matrices, and then what is this used for? Matrices are used for much more than just solving linear equations like we did last time. I'm going to go through a couple of applications and specifically focus on transformations. Okay, so we're going to start with addition of matrices. To add matrices, you basically add the terms of them, and they have to be the same shape to do that. So let me give a couple of matrices up here. Let's call A 1, 2, 3, 0, and B we will call -1, 2, -1, 3. So first of all, they have to be the same size in order to add or subtract them. This is a 2 by 2 matrix. Remember, that's 2 rows and 2 columns. This one is also 2 by 2. They are the same size, so you can add them. What you do to add them, and there's notation in the notes for this, but let me just do an example. You just add the corresponding terms. So this one over here, for example, A11 gets added to B11 over here, which is -1. So A plus B is equal to 0, 4, 3 plus -1 is 2, and 0 plus 3 is 3. And then if you want to subtract, for example, A minus B, you just subtract the corresponding terms. 1 minus -1, which is 2. Put that over here as well, 2. 1 minus -1, 2 minus 2, which is 0, 0. 3 minus -1, which is 4. And then 0 minus 3, which is -3. So there we go. This is adding and subtracting. Pretty straightforward. I'm going to give you some examples now to work on. So erase this. I'm going to put a couple different matrices up. Again, let's do some 1, 2, 5 of A, and let's call B 3, 2, 1. Okay, so what I want you to do is solve for A plus B and A minus B. I'm going to pause it here and do those problems. I'll come right back. Okay, so let's check the answers. A plus B should be, again, adding corresponding terms. 1 plus 3 is 4, 2 plus 2 is 4, and 5 plus 1 is 6. If I want to subtract, 1 minus 3 is -2, 2 minus 2 is 0, and 5 minus 1 is 4. Again, note they have to be the same size. This is 3 by 1. That's 3 by 1. And my answers are also 3 by 1. If they are different size, for example, if I just did like this, and make this say 2, 4, 5, and made it a 3 by 2, the answer to how you add them and subtract them is simply does not exist, does not exist. You can't do it. Okay, so that's addition and subtraction. Now we're going to move to multiplication. The first kind of multiplication is called scalar multiplication. You'll see that in the notes. It's SCALAR, multiplication. That means multiplying by a number. On the outside. So, for example, 2 times the matrix 1, 2, 3. What this means is you multiply 2 by all of these, you get the matrix of the same size when you're done. So it's just 2 times 1 is 2, 2 times 2 is 4, and 2 times 3 is 6, like that. This is a number times a matrix. Okay, now a couple combination examples of that. I'm going to do the ones in the presentation, and I'll have you do them. So if I have A as -2, 3, 0, 1, B as 8, 1, 5, and 4. And what I want you to do is, first of all, tell me what A plus B is, and then I want you to tell me what 3A plus 2B is. Okay, pause the video, do that problem. Okay, and then you're back. Now I'm going to do A plus B. So A plus B is -2 plus 8, or 6. 3 plus 1 is 4. 0 plus 5 is 5, and 1 plus 4 is 5. 3A plus 2B, you take 3A first, and then add it to 2b. So 3a is just 3 times all of these numbers. -6, 9, 0, and 3. And then 2 times b, which gives you 16, 2, 10, and 8. And then finally we have to add them. -6 plus 16 is 10, 9 plus 2 is 11, 0 plus 10 is 10, and 3 plus 8 is 11. And there we go, hopefully that checked out. Okay, the last multiplication we're going to do is matrix multiplication. So let me erase this. Matrix multiplication. This is the most complicated one. I do look through the notes first to give an example of how you do it, but let me give you an example with numbers. I'm going to take the example again from the notes, which is a of 3, -2, 1, 5. Sorry for the presentation, not the notes. B is 0, 0, 5, -6. So a matrix multiplication means multiplying a matrix times another matrix, not a number times a matrix. So I've got a 2 by 2 here, and I'm going to multiply by a 2 by 2. So first of all, the only way you can multiply matrices together is if the inner terms, when you multiply these out, are the same. And you'll see why when you multiply. It must be same. So if it's 2, this has to be 2, or you can't multiply. The outside numbers, here and here, give you the output size if you multiply them together. In other words, if I multiply a 2 by 2 by a 2 by 2, I get a 2 by 2. And I'll do a couple examples that show that. Okay, so now how do you do it? Let me write them down again. So I'm going to do a times b. The basic idea of matrix multiplication is to do row times column and do it 1 by 1, 4 times in this case, until you get all the numbers. So what I mean by that, I'll do an example. Here's the first row, so row times column. I'm going to multiply the first row times the first column. 1 row, 1 column gives me element 1, 1. And then what I do is I multiply the first number times the first number in the first number in the row times the first number in the column, and I get 3 times 0. And then I add to that the second number times the other one, so -2 times 5. I'm going to run out of room here, unfortunately. I'll put the rest of them down here. So again, 3 times 0, -2 times 5. And that will give you, when I'm done, if I just do this together, 0 minus 10, or -10. That is just for the first element. Now if I want this element over here, which I'm going to write down here, unfortunately, because I ran out of room. Actually, I'll just erase this and put -10. Then I can just put it on the same row. -10. Now I'm going to write the first row times the second column. So 1 times 2 gives you 1, 2, which is over here. So 3 times 0 plus, again, plus -2 times -6, which is 12. So this becomes 12. Okay, I'm going to put 12 up here as well, so I have room. 12. Okay, then I want to get the second row. I'm now going to take the second row and multiply by the first, and then subsequently the second row of the first column. So row 2 times column 1 will give me 2, 1 element over here. So 1 times 0 plus 5 times 5, or 25. And then finally do the last thing, erase that, 25, which is row 2 times column 2. 1 times 0 plus 5 times -6, which is the -30. Like that. Okay, and now I'm going to do b times a. For one thing, just to show you that they're not the same, I'm going to put a times b down here. I'm going to erase the middle part here, and I'm going to do b times a. Okay, so I'm going to rewrite them, and I would always suggest doing this. 0, 0, 5, -6 times 3, -2, 1, 5. Again, 2 by 2 times 2 by 2 will give you a 2 by 2. Now let's go through the multiplication. Again, the first one is row 1 times column 1. So 0 times 3 plus 0 times 1. That is 0. Same thing with the second column. 0 times negative 2 plus 0 times 5 is 0. Okay, now go on to the second row. 5 times 3 is 15. Negative 6 times 1 is negative 6. 15 plus negative 6 is 19. And then 5 times, last one is this one. 5 times negative 2 is negative 10. Plus negative 30 is negative 40. Okay, and notice that b times a is not like a times b in any way. So multiplication by matrices is not commutative. In other words, like in real numbers, 2 times 3 is 3 times 2. B times a is not a times b, except in very special cases. So can't assume they're the same. Okay, I'm going to give another example for you guys to work through. Erase this as well. It's different sizes. So we'll go A is 1, 2, 3, and B is negative 1, 0, 5. What I want you to do is, oops, that's not right. That's not going to work at all. Negative 1, 0, 5. So we have a 3 by 1, and we're going to multiply by 1 by 3. Okay, so what you do is to find AB and BA. Pause the video and do those for a moment. Okay, if you're back, we're going to go through those now. A times B, first of all, that is a 3 by 1 by 1 by 3. Notice that these are the same, so that means we can do the multiplication. And the result will be a 3 by 3. So I'm just going to write a big 3 by 3 up here. That's going to be my result, 3 by 3. So now I do row 1, which is only one number, times column 1, which is only one number. So it's 1 times negative 1. Then row 1 times column 2, 1 times 0, 1 times 5. Okay, that's your first row. Now go to your second row, which is just 2, and multiply that by each column. So you get 2 times negative 1, negative 2, 2 times 0, 0, 2 times 5, 10. And then finally 3 times negative 1, negative 3, 3 times 0, 0, 3 times 5, 15. Notice that I'm not adding any of the numbers like I did before. That's because it's row 1 times column 1 is only 1 times negative 1, and that's it. There's nothing to add. Or 1 times 0, that is actually row 1 times column 2, which gives you element 1, 2. And therefore you're just doing 1 times 0, not adding it to anything. Okay, b times a, I'm going to write it down just to see what happens here. But first of all, you get now a 1 by 3 matrix, and you're multiplying by this is 1 by 3, and you're multiplying by 3 by 1. This again says you can do it. The 3 is the same. The 1s on the outside tell you you're going to get just one number left, 1 by 1 matrix. And you get that by doing row 1 times column 1, which is negative 1, plus 0 times 2, which is 0, negative 1 plus 0, plus 15, which is 14. Just one number. Okay, that's basically it. There's a series of charts in the notes or in the overhead, the PowerPoint, that you should look through that tell you what properties matrices have, but just as a summary, for addition, a plus b does equal b plus a. In other words, you can reorder addition, but a times b does not equal b times a, which we just demonstrated. That's called the commutative property. There's also several others in here. There's the associative property, which just says a plus b plus c equals a plus b plus c. You can do these in an order, or you can add a plus b first before adding c, or you can add b plus c first and then add a. And that works for multiplication as well. As long as you keep the order the same, because the order matters in matrix multiplication. But you can group them differently. In other words, over here, I can multiply a times b, and then multiply that by c, and I'll get the same thing if I multiply b times c, and then I multiply a as long as the a is in the front when you do it. But then also, there's a distributive property, an inverse property, and an identity property that you should look through and make sure you take notes on those when you go through the material. Okay, we're going to move on to applications of matrices. So applications. So I'm going to go through two. The first one is going to be transformations. Transformations are largely done. So transformations, do the first one. Transformations, if you recall, are transformations are translations, reflections, rotations, and dilations. Transformations are used, we've already used them to transform functions, and we did in geometry to transform figures. The real way they're used today is largely through computer screens and cell phone screens. And they're done entirely by matrices. So I'm going to give you the equations that show it. And then I'm going to give you an example, a simple example that's in the presentation. So first, translations. Left, right, up, down. And this is in your notes as well. If you have a point that you have, and you want to translate it, say you have a point like, I don't know, it's on your television, say it's on your cell phone screen, it's like 50, 100. Which on your cell phone screen, by the way, for the big screen over here, 50, 100 would be 50 on X and 100 like the dot right here on your cell phone screen. At 50, 100. If I want to move that dot, say I swipe my finger across it, and I want to move it, say, over here, assuming, for example, that this is X and this is Y, I can just move it, say, over 20 pixels and up 20 pixels, and I will add 20, 20. This will be my right-left motion, adding to the X. This will be my up-down motion, adding to the Y. And maybe I should use a different number, 20, 30, say. So that means my new point, after I do that, will be 50 plus 20, or 70, and 30 plus 100, or 130. So that's how transformations work, or translations work. You simply add the movement you're doing, which is usually a movement of your finger across your screen, to the original number. Okay, now we're going to do reflections. I'm going to use that same picture over there. Reflections. So reflections, you have so again, trying to find a new point, from a translated point of -1, 0, 0, 1. Let's see, X, Y. So the way you reflect, and this is reflected across the Y-axis, the X-axis is Y-axis, you do a matrix multiplication. So I've got some point like, I don't know, 50, 100. And I want to reflect it across the Y-axis, which is actually over here. So you're actually creating a point over here, which doesn't really exist. But you would actually, when you typically do this, you'd actually define the origin to be over here. So the reflection actually still results in the object being on your screen. Okay, so anyway, it's matrix multiplication. I do -1 times 50, which is -50, plus 0 times 100, row 1 times column 1. And that gives me -50. Then the bottom row gives me 0 times 50, plus 1 times 100, 400. And that point is now over here. I've reflected it. If I want to reflect across the x-axis, by the way, all the changes in this matrix, so this is y-axis, I want to do x-axis reflection, otherwise go this way. The only thing that happens is I do that. And that's the new matrix for that. Okay. Rotation is the next one. This is a little more complicated one. So this is if you want to like spin an object around itself. And again, this is in your notes. I'm just rewriting on the board so I can talk through it. Again, it's a matrix multiplication of your point, like 50, 100. And this matrix of sines and cosines. Now remember from first semester, if I wanted to say rotate 90 degrees, I could put 90 in here. So this is just an example. I'll make it equals 90 degrees. Cosine of 90, hope you remember this from the unit circle. Cosine of 90 is 0. So that's 0, 0. Sine of 90 is 1. So this is -1. Sine of 90 is 1. There we go. That's a matrix multiplication. And I'll go 0 again. Now matrix multiplication will give me 0 times 50 plus -1 times 100, and you get -100. And then the second row is 1 times 50 plus 0 times 150, -150, which is -100 and 50 over here. So that's a rotation of 90 degrees counterclockwise. Now the benefit of this, we did this before when we were doing in geometry. But the benefit of doing this is I don't have to put 90 or 180 or 270 or 360, which is what I did in geometry. I can put any angle I want in, like 20 degrees, for example. Okay, that's rotation. Last one is dilation, which is the simplest one. This grows the figure. The matrix equation for that is x prime y prime equals k x y. So if I want to grow this point, for example, by 5, let's say I'm going to triple it. So I make k 3. I still have my point 50, 100. That becomes therefore 150 and 300. Just moves it out here someplace. Move it away from the origin further out. And I can move a whole object by just moving multiple points, not just one. Okay, just one final thing on the transformations. This is a single point. Your screen is obviously a much bigger thing. It's 400 pixels by 600 pixels, which is, was that 24 with 4 zeros on it? 240,000 pixels. And what you want to do is actually move those simultaneously, or transform them simultaneously. What you do then, if you look at the notes, there's a picture of it. There's a picture of an L moving. You actually create a big matrix. For example, let me give you the matrix of what is an L in the letter L. It's like this on a grid. And this, for example, is 0.30. This is again from your presentation. And this is 0, 0. The way I put these into a matrix is I don't put x, y at just one point, like that, which is what we had before. I put a series of x, y's, like 0 and 0, for example. And then 3, 0, like this 2 points. And then notice this also, this is 3, 1 is another point. 1, 1, 1, 5, 0, 5. So there are 1, 2, 3, 4, 5, 6 points. If you did this on your screen, for example, this would be 240,000 columns by 2 rows. And that's what your screen is represented to on your cell phone, for example, or your computer. Now, if you want to transform these, all you have to do is, for example, let's say I want to take your whole screen, you swiped it up, and you moved it over, let's say up 50 and say right 50 and up 10. So what I would do to do that, remember the transformation is just the points of x, y plus your transformation. Problem is this is now 2 by 6 in this case, or in your own screen, 2 by 240,000. So what you do is you actually create a matrix like this, the 0, 3, 3, 0, 0, 1, 1, 1, 0, 1, 5, 5, and you add to it up right 50, up 10, except you do it with, to make them the same size, like that. And that allows you to add 50 to every one of those x's, and you'll get 50, 53, 53, 51, 51, and 50, and add 10 to every one of those y's. So you get 10, 10, 11, 11, 15, 15, and this is your new point, which will move the whole object over. This L will just go right 50, up 10. Okay, that's it for transformations. Look through the notes, by the way, to see some problems on that. You know, I'll work through them. The last thing I'm going to go through is physics equations. I'm sure you're familiar with this. Force equals mass times acceleration. This is, however, in high school math, typically written as a simple linear equation, where that's one number, and that's reality is, F has 3 dimensions. Force in the x direction, force in the y direction, and force in the z direction. Mass is one number, it doesn't have 3. And then acceleration is acceleration in the x direction, acceleration in the y, and acceleration in the z direction. In other words, every physics equation is actually 3-dimensional. It's actually a matrix equation, not a linear equation. There's another example in the notes, again, I'm sorry, in the presentation, which is torque equals I alpha. This is called the moment of inertia. This is torque, which is rotational force, and that's rotational acceleration. Torque, again, has 3 dimensions. You can rotate in a force in 3 different directions, x, y, and z. Moment of inertia actually is a 3 by 3 matrix. It's completely filled out like this. Z. You can see it in the notes, etc. And then over here, a rotational acceleration also has 3 dimensions. So this is matrix multiplication, and this very simple, if you have physics or physical science, this simple linear equation is actually a 3 by 1 equals a 3 by 3 times a 3 by 1. A very relatively more complex matrix equation. Okay, that's it. Work on homework 23, which is matrix operations, and drop me a line if you have any questions. Thanks.